So once again, welcome you all for the DSP lectures. And today we'll take up two more examples on the impulse invariance method. Now take down this particular problem. The system transfer function of an analog filter is h of s equal to 1 whole divided by it is 1 divided by s plus 1 into s plus 2. So this is h of s is equal to 1 divided by s plus 1 into s plus 2. So obtain h of z, which is nothing but a digital filter using impulse invariant technique. Assume sampling frequency of 5 samples per second. Now, in the derivation part, we have derived h of s is equal to. So we took the example something like this where k runs from 1 to n. So for nth order generalization, the we have ak as one of the pole and capital AK as the gain of the filter. Then where n is the root of the characteristic equation or total number of poles in other way. So when I move to h of z, so this I derived in such a way that so this was ak whole divided by 1 minus e to the power of minus akt into z inverse, right? Or else if you remember this equation, then minus spt into z inverse, where sp equal to minus ak in this case, right? So here sp is equal to minus ak. So that's what the transformation was all about, which means to say that. So again I can take this k runs from 1 to n, so which means that my equation should be like 1 s plus, so let me assume one of the pole like sp1 plus summation. If there are n equal to 2, let me assume second order filter, then probably numerator, let me assume this. So this is how I should have, right? So this is the way for uh, uh, for the system to be represented as h of s. But look at the problem statement, how it is. So it is a factor of s plus 1 into s plus 2, which is nothing but a one quadratic equation that we have. So now by looking into this equation, I can say that the order of the filter is 2 because s into s square. So characteristic equation is quadratic equation. So which means that there will be a two roots. So here also you can observe that s equal to minus 1 and s equal to minus 2. One pole is lying at minus 1 position and another pole is lying at minus 2 position. That is what the meaning here, right? Now until and unless I have the roots, because we have a direct equation to write h of z, which will be in this form, assuming that this will be in this form, but it is in the form of factored. So I need to go for factorization of equation number 1. So let me assume this is equation number 1, that which means I need to since the roots are repetitive, there are two roots, or not repetitive, there are two roots. One is at minus 1 and another one is at minus 2. So obviously a technique that I'm supposed to solve for partial this one is I will be applying partial fractions initially. Apply partial fractions. So why we go for partial fractions? Because I must get my equation standard h of s in summation form, in this form. It is not in summation form, it is multiplicative operations. So I want this rather than in this form, because I have a ready-made equation h of z equal to in this fashion I can apply. So directly here I cannot apply with which is having a multiplication operation like this. So hence I will be adapting a partial fractions for this method. Okay, that is h of s is equal to 1 by s plus 1 into s plus 2. So in apply partial fraction method for this. So that is h of s is equal to a divided by s plus 1 plus b divided by s plus 2, right? So find out the value of a and b. Find out the value of a and b. How do you find? So that's where 1 is equal to, what is that, a into s plus 2 plus b into s plus 1, right? 1 divided by s plus 1 into s plus 2 is equal to, this is the h of s equation. So this is going to be written as a divided by 1 plus s plus b divided by s plus 2. Now, so 1 is equal to a into s plus 2. I hope you remember the method how to solve the partial fractions here. So now put or let s equal to minus 2 so that a becomes 0. I am going to get the value of b. So this is 1. So a is equal to minus 2 plus 2, because I am trying to put s equal to minus 2 here. So this is b equal to minus 2 plus 1. So where therefore the value of b I am going to get it as minus 1, right? Similarly, put s equal to, so I need to make this term as 0. So which means that what I should put minus 1 here. So put s equal to minus 1. Therefore, in turn, if you solve this, you will going to get a equal to 1. Okay. So since you know the partial fraction method, so I don't waste much time in this step. Therefore, what is the h of s now? H of s equal to 1 divided by s plus 1, first factor, and second one is 1 divided minus 1. So that is, therefore I put minus here, and this is s plus 2. Now look at this, you can easily go for taking inverse Laplace transform for this, right? I don't have a inverse Laplace transform for 1 divided by s into s plus 1 into s plus 2. But I have a Laplace transform, inverse Laplace transform for this, which is of the form 1 divided by s plus a, where if you take this, it is e to the power of minus at is the standard inverse Laplace transform, right? Similarly, that's what we derived in the last class, right? So where I can write directly h of z in this form fashion. So, we know that if h of s is equal to 1 divided by s plus ak. So instead of going for h of d, I directly write h of z, because we already derived this from impulse invariance method technique, right? So directly from Laplace to zt. See, inverse, instead of going to inverse Laplace transform and again applying the z transform, I already solved this by considering as a standard example in the derivation itself. The derivation says that, so this will be equal to 1 by 1 minus e to the power of minus akt z inverse, right? Go back to your derivation. So this we already solved. Okay, I have a Laplace transform in this fashion, and I can able to write that in this particular fashion. Now of such there are two values. Now you need to represent this 1 by s plus 1 and 1 by s plus 2 in the form of h of z. That's it. So that we will try to do. For first value, let me write this once again, 1 by s plus ak. When I move to z transform, I can write able to write this as 1 by a power a to the power of minus akt into z inverse. So the first term is 1 by s plus 1. So if I want to write this in this fashion, what is AK here? AK equal to minus 1, right? So I'll write this as 1 minus e to the power of minus AK value, see, AK value is 1, not minus 1. AK value is 1, so I'll just write e to the power of minus t and z inverse, right? Okay. Now what about s plus 2? So this is zt 1 divided by 1 minus e to the power of minus 2 times t into z to the power of t. So, which means that h of z is equal to 1 by this minus 1 by this, right? Apart from that, he has also given me, look at the question, he already given me the sampling rate also, or sampling frequency. If you observe here, he has given you the frequency, sampling frequency fs is supposed to be 5 samples per second, right? From this you are supposed to obtain the capital T. What is capital T? 1 by fs. So this is equal to 1 by 5, right? So you already have this T value which is given in the question. So this T value he has given sampling frequency value. So sampling frequency has given fs, which is 5 samples per second. So therefore if I calculate for T, so this will be 1 by 5. And what's the 1 by 5 there? Z 0.2, right? So this will be equal to zero point 0.2. Now just substitute this value here. So that is, I'll just make a point here itself. 1 divided by 1 minus e to the power of minus 0.2. That's the value of t. Now calculate what is e to the power of minus zero point 0.2. Just I'll pause the video. Yes, the value of e to the power of minus zero point 0.2 is 0.818. So that I'll write here 0.818 z inverse. And then, so this once again e to the power of 1 minus e to the power of minus 2 into the value of t is once again zero point 0.2 z inverse. So 2 into zero point 0.2 will going to give me 0.4, and I need to calculate 0 e to the power of 0.4, that gives me 0.6703 z inverse. Now how do you write the h of z? H of z is equal to 1 divided by, first I need to write the 1 by s plus 1, right? So look at this. So this is h of z is equal to 1 by s plus 1's z transform and 1 by s plus 2's z transform. That's it. 1 by s plus 1's z transform is nothing but 1 minus 0.818 z inverse minus 1 divided by 1 minus 0.6703 z inverse, right? So look at your h of s value and h of z value. So h of s is nothing but this, okay? Separately I took z transforms of 1 by s plus 1 and 1 by s plus 2, and I put t equal to 0 1 by 5 because fs is given as 1 by fs is given as 5 samples per second. That gives me zero point 0.2 seconds, right? So here initially for this 1 by s plus 1, so 1 is ak equal to, the first pole lies at ak equal to 1 and the second pole k1 and k2, let me take here, that is 1 and 2. For that I will be substituting here. Here a power k is 1 and here in this case a power k is 2. Then it is going to be a, for this case here e to the power of 0 point, minus 0 0.2. Put it this value in calculator, we are going to get 0.818. Similarly, e to the power of minus 2 into 0.2, that gives me e to the power of minus zero point 0.4, and when I put it in calculator I am going to get 0.6703. Okay, now individually we got 1 by s plus 1 and then 1 by s plus 2. That once again I try to write it in the form of h of z. That's it. So let me go for more simplification by taking the LCM of this. So that is 1 minus 0.6703 z inverse minus 1 minus into minus, that will going to give me a plus 0.818 z inverse whole divided by this into this. So let me multiply this. 1 minus 1 into 1 1, so 1, this is minus 0.6703 z inverse. Next, minus 0.818 z inverse, minus into minus plus 0.818 into 0.6703, 0.818 into 0.6703, we're going to get 0.548 to the power of into z to the power of minus 2. Simplify this, I'm going to cancel out plus 1 and minus 1, and finally write the equation here. Minus 0.6703 z inverse plus 0.818 z inverse. So in the numerator I'm going to get 0.147 z inverse. So 1 minus, in the denominator 1 minus, so again, so this will be 1.4 minus 0.6703 minus 0.818, so that will be minus 1.48 z inverse plus 0.54 z to the power of minus 2. So this will be the final h of z. So once again I'll write it here. Final value of h of z is 0.1477 z inverse divided by 1 minus 1.44, sorry, 48 z inverse 0.548 z to the power of minus 2. Any doubts? So look at this. How do you implement this in terms of hardware? So here it is z inverse. So one delay factor is 0.14, right? Which is nothing but one flip flop I should use here, and followed by, so the you know already the cascading, right? Cascading technique that you already learned in the lattice structure that you learned in the signals and systems, where you try to write this as input. So this is output by input function, right? So this is x of n and this is y of n denominator, right? So when you try to write this h of n, so you're going to get in terms of h of n. So again, if you go for taking inverse z transform, so now this is currently this is in terms of frequency domain. Now if you want to get back in terms of time domain, so just go for taking inverse z transform. You're going to get h of n. H of n, once again, uh, output will be in the form of y of n divided by x of n. Output to the input, output by input, right? So this input will be a signal followed by with a negation. So one more adder or a subtractor you need here. Then one delay unit is required. So Z inverse. One delay unit is nothing but in terms of digital, it is flip flop. One flip flop is required here to generate this much amount of delay. Then followed by, so already we have a one delay here. So put one more flip flop. So I am going to get a two delays, right? And across the output I am going to get in this form, right? So that's how we try to design a digital filter. So the thing is, we have a transfer function in terms of Laplace domain. The reason is Laplace give me a continuous time function. Whenever a signal is continuous time function, I apply a Laplace transform for this signal, then I'm going to get the output transfer function in terms of h of s. Then later on, to design uh, h of z, I am in this particular example I am inculcating impulse invariance method, so by through which I obtain the h of z. So here there are in this particular example, the roots are two roots. The one is at -1 and another one is at -2. Hence, we adapted the technique called the partial fraction methods to obtain the value of a and to obtain the value of b. So once you obtain the value of a and b, put this uh, in the h of s, and finally uh, try to obtain the value of h of z. That's it. Note down this example. Second example, design a digital filter for a given analog filter. Assume the sampling rate frequency Fs equal to 8 Fc, where Fc is nothing but a cutoff frequency. So let me draw the circuit here. So this is the circuit, one capacitor. I took a very simple example here. I think you might have saw this circuit while demodulation, modulation and demodulation technique in your communication lab. So this is V1 of t, and this is my output V2 of t, 1 farad capacitor and 1 ohm resistance value. So this is R, this is XC, right? Now design the digital filter for this. So how do you design the digital filter? Just I need h of z, that's it. Later point of time, that's inculcating of the the flip flops, that's it. But I should understand that how do we solve this example. Here you don't have, first of all, you don't have a h of s itself in the question. You need to formulate the h of s. What do you mean by h of s? Basically, a transfer function. What do you mean by transfer function? Output by input. Try to understand this. I'm trying to take up this exam. I'm trying to give this example because it gives you a more realistic. So I'm trying to connect your network analysis or in terms of analog circuits, and how actually we construct analog filter to a digital filter. So this is a filter which is nothing but the high pass filter here basically. Now I'll ask you the one question. Okay, before moving, what is the order of this filter? What is the order of this filter? I'll come to chat room. Let me see what's the answer. Okay. So here V2, so V2 of t divided by V1 of t. So how do we write this? So this is nothing but V2 is voltage across this point, that is voltage across R. I simply write this as R, and V1 of t is nothing but XC plus a voltage across the resistance, that is XE plus R, that is output to the input. So once again, V2 by V1 of t is nothing but R divided by XC plus R. Now this is in terms of time domain. So I need to move for the frequency domain from time domain. So for which I will be applying the Laplace transform for the same. So now h of s is equal to V2 of s divided by V1 of s, that's equal to the Laplace transform of resistance R is 1. The Laplace transform of XC is 1 by S. So now I replace my R by 1. It is its equivalent Laplace transform, and XC by 1 by S. Its equivalent Laplace transform. Once again, 1 for Laplace transform of resistance. So now moving further, h of s equal to output by input v2 of s divided by v1 of s, that is equal to 1 divided by 1 by s plus 1. So when you solve this, you will going to get s divided by 1 plus s. So again by equation also I can able to see that the order of filter is 1, because s to the power of 1 in the numerator as well as in the denominator. Now once again it is not in the form of standard form, because we know that h of s, if I have a h of s in the form of ak divided by 1 minus s plus ak, then I can easily write or transform this to z transform in the form of h of z is equal to 1 divided by 1 minus e to the power of minus akt into z inverse. This is how I can able to transform. But here in the numerator I have s, which means that either you go for partial fraction method, or here it is very simple, I will go for long division method. You can go for partial fraction or you can go for finding the value in terms of long division method. So how do you write this in terms of long division method? So this is s plus 1 s, right? So what is the value that I need to put? S into 1 is s, 1 into 1 is 1, right? So change the sign, this will get cancels, this is minus 1. So how do you write this? 1 by 1 minus 1 minus 1 divided by s plus 1, 1 divided by s plus 1, or 1 plus actually ಇಲ್ಲಿ minus ಇದೆ, directly I'll put minus here. So this is the form. So therefore I can write h of s, I have h of s is equal to 1 divided by s plus 1. I can, after long division method, I can rewrite this as 1 minus. Oh. So this is somewhere else, like I'm trying to take proper, it is not a proper fraction, it is basically improper fraction. Now I got it in terms of proper fraction. So this is my proper fraction. Now this is h of s value. Now it is very easy for you guys to solve this or to obtain h of z. Now quickly obtain the h of z value for this. The point is very simple. If you take even the inverse Laplace transform of 1, the inverse Laplace transform of 1 is 1 itself, because the Laplace transform of 1 is 1. And you also know that the inverse Laplace transform of this one is equal to 1 e to the power of minus 80, right? So s plus a, or else directly I have the value. How I can be able to write this? This already you know how to write this in the form of h of z. Try to write it. So we have 1 divided by s plus 1. So if I try to write this in terms of z transform, how do you write? 1 divided by 1 minus e to the power of minus a. A value here 1. So therefore minus t z inverse. That's it. Right? So finally h of z can be rewritten as h of z equal to 1 minus 1 divided by 1 minus e to the power of minus t z inverse. Now what about t equal to? What is t? T is given in the question. Let me check. T is given as the sampling rate is 8 times Fc, cutoff frequency. So Fs is equal to 8 Fc. He has not directly given the Fs value, but we know that the cutoff frequency Fc is given by what? Fc is equal to,
1 by omega c.
yes, very good, 1 divided by omega. Omega can be written as 2 pi 2 pi r into c, right? Because I have the resistance value and capacitance value in my circuit. So that's where I try to put 2 into pi into R into C. What is the value of R and C? Both are 1, I think, here in my case. So this is 1. Try to find out the value of Fs and get me the answer. 8 divided by 2 pi. So which is nothing but 2 ones are 2 fours are 4 divided by pi. What is 4 divided by pi? Fs value quickly.
1.273.
Good. It is 1.273 samples per second. So therefore T is equal to 1 divided by 1.273. This is equal to how much?
0.785.
0.785. So this is 0.785 seconds. Put this here. So therefore h of z is equal to 1 minus 1 divided by 1 minus e to the power of minus 0.785 z inverse. Put this value here. 1 minus 1 divided by
0.56.
1 minus what? Point. Am I right? Okay. Now rewrite this. I'll take a LCM. 1 minus 0.456 z inverse minus 1 whole divided by 1 minus 0.456 z inverse. So plus 1 and minus 1 get cancels. Therefore, final h of z is minus 0.456 z inverse divided by 1 minus 0.456 z inverse. So now this is your digital filter. See here, in this example, we have not given you the h of s value. We have given you the circuit itself, which means by looking into that particular equation, if any equations are present like this, see here, if any equations are present in this form, you should imagine that there exists a one capacitor or one inductor value. So accordingly, you need to solve this example. If you come up with this h of s in this form. Of course, if I look into the only mathematical direction, so it is only a simply a characteristic root or a characteristic equation for me, one simple polynomial equation. Now, what happens here if we don't adapt it to the circuit or the engineering aspects? So we will be learning Laplace as an independent subject and mathematics as an independent subject and Z transform as an independent subject. We don't try to correlate. So that's where I call it as a gap, filling the gaps. So you need to connect dot by dot. So till now you were knowing that Laplace was restricted to control systems and network analysis, and Z transforms were restricted to signals and systems, right? So in this, I think I can able to give you the clear understanding of the analog circuits, followed by how I can able to use the Laplace for the same. Then how analog circuits can be converted into digital circuits. So here it is very simple here onwards. So like later point of time, we have one more chapter where I try to give you how to write this in the form of lattice structure or cascading form. So there I will try to write you one simple. This already you have learnt it in your signals and systems how to represent in the form of the bus, like with what we call it as cascading lattice structure. So that itself, where a z inverse indicates that one simple delay over that. To generate that amount of delay, what we need to do is, so we apply a flip flops, because flip flop is one which is going to be called as a delay element, right? That's it. Any doubts here in this case? If you if you don't have any doubts, I have a small example for you guys to solve this on your own. uh, for h of s equal to, consider h of s is equal to s plus a divided by, in the last class I solved this. Now you try to apply the what is that, partial fraction method, to obtain h of z. Obtain h of z for this. Okay, now you need to solve this, because look at this in the denominator. You once again, you don't have a standard form directly, you can so that you can directly apply the h of z value. You have a standard formula to apply only if and only if you get a h of s in this form. ಈ ತರ ಬರಬೇಕು at any point of time, in the form of summations. So only then I can able to apply uh, h of z directly. So unless you need to go for a partial fraction method, or if you know the inverse Laplace directly, you go for inverse Laplace and sample that for nt times, then you apply the z transform, for which you need to know standard values, or else better you go for partial fraction method. Okay, solve this by partial fraction method. If you want, I'll just solve this halfway, and later on you can recollect the steps and solve this. Okay, so first let me go for s plus a. So here I have a plus b whole square. Let me start this like a square plus 2 times of as plus a square plus b square. Okay, now what happens here? What happens here? Right. Try to recollect this, or else sorry, the other way I can see here, the 1 divided by s plus a whole square plus b square, right? So I think I'll call this as a square plus, if I call this x square plus y square, I don't have a formula for, I have a formula for x square minus y square, but I don't have a formula for x square plus y square. So what I do is, somehow I try to make this to behave like a square minus b square formula. So what we do is, we'll remove this. So h of s is equal to s by a. This is one small modification that we have to do here. So I write this as s plus a whole square as it is. Okay. Now what I can write, b square plus b square idea. So can I include minus j square here? What is what is j square? Minus 1. Minus 1 into minus is once again plus. So this will not disturb my original equation, right? So this will be again my original, as same as my original equation. Now it is very easy for you guys to apply a square minus b square formula. You apply this a square minus b square formula, s plus a divided by, so this will be s plus a plus jb into s plus a minus jb. Okay, now this is very easy now. So now you got in terms of roots of the characteristic equation. Now the pole lies in, one of the pole lies at minus a plus jb, right? So another pole lies at minus a minus jb, right? So both the poles are real values are on the left hand side, hence the system must be a stable system. Oh, that is for sure. Now apply the partial fraction method and obtain the values of a and b. So that is s plus a equal to a into s plus a minus jb plus b times s plus a plus jb. So probably you will going to get a and b both are 1 by 2. Okay, solve this, then you adapt the method, a and b both will be equal to 1 by 2. Okay, so solve this. So again you repeat the process that what we have done. Okay, that I think further it will be very easy for you guys to solve this example, right? So if I write this h of s after obtaining, we'll just write like 1 by 2. So you can solve this later on. So this is one factor plus, right, 1 divided by s plus e minus. So this is ak value, one of the pole, and this is another value. Okay. So how do you map this to e to the power of minus sp? So one of the pole s1, let me call this. So this is minus a plus jb, right? So here z1 equal to e to the power of minus a plus jb into t. Am I right? So this is how you are supposed to write. Okay, minus a plus jb. So second pole s2 equal to minus a minus a minus jb, minus a minus jb. Therefore z2 second is equal to e to the power of minus j minus jb, so into t here. So this is e to the power of akt. Okay, so try to write the value, try to write the h of z for the same. Okay, so h of z 1 by 2. So if I write this 1 divided by 1 minus, directly I am writing e to the power of minus of, I take this plus t, e to the power of t z inverse plus 1 divided by 1 minus e to the power of a minus jb into t z to the power of minus 1. Solve this. Partial fractions, no, sorry, take LCM and solve this. So this will be coming in terms of cos, because in the numerator you will going to get the definition of cos e to the power of j theta plus e to the power of minus j theta divided by 2, because anyways here you have a 2. So you just make sure, ensure that it will be in terms of cos theta. Okay, so that's it for the day. So this is how we are supposed to calculate the uh, h of z value for a given Laplace transfer function. Okay, so I'll stop. If you have any doubts, please let me know, or you can put it in chat box now. And just pause the video recording. Thank you.